Welcome to Homework Lib.
This question regards the Zeeman effect or Zeeman splitting, and it asks if we have a gas that is undergoing a P to S transition that emits a certain wavelength, plus or minus a little bit, resulting in a 3-band wavelength. This asks what the magnitude of the external magnetic field is. So, Zeeman splitting says that energy levels of electrons split and enter new discrete energy levels under the influence of an external magnetic field. So, given our initial wavelength of 575.05 nanometers, that splitting occurs and causes two new wavelengths to come about that are 0.0462 nanometers away. The question again asks, what is the strength of the magnetic field? So to do this, first we need to understand what the energy is of a single photon, and that is going to equal hc over lambda. Now, we can see that we can get a few different energies from this problem. We have our initial wavelength, and then we have an excited state and a slightly disexcited state. The longer wavelength will be more energetic, and that's the one we're going to use to solve the problem, but you could use the other one as well. So, our initial energy, which we will label EI, using Planck's constant, which is 4.14 times 10 to the minus 15 eV, and the speed of light, divided by lambda, which is just going to be our 575.05 nanometers. If we plug all of that in, we end up getting 2.1981 electron volts. That is the energy of our ground, if you will, state photon, the unexcited photon. Now, our final energy, we can choose either of the different bands. We're going to choose, in this case, the higher wavelength band, so adding 0.0462. If we do this, we have a slightly higher wavelength, which ends up being 575.0962. And if we do the same calculation with H and C, we end up getting 2.1964 electron volts. So our change in energy is going to be E initial minus, or rather E final minus E initial is our change in energy, delta E, and that is equal to 0.0017 electron volts. What can we do with this? Well, there is something called U, and U is defined as the energy of interaction with a magnetic field. In other words, the amount of energy that the magnetic field can impart on a photon. So, after this interaction, based on Zeeman splitting, U is the amount of energy gained or lost. So, that is going to be equal to delta E. And U is similarly defined as negative mu Z times the magnetic field, where mu Z is equal to negative ml mu B. Mu B is the Bohr magneton, and that is another constant equal to 5.788 times 10 to the minus 5 electron volts per Tesla. Going through here, we can then solve for B, the magnetic field magnitude, And that is going to be equal to delta E divided by ml times mu b. Now, the only thing we have left to determine is what is ml. Well, we started off in the p state, and so for the p state, n is equal to 2, L is equal to 1, and ml, therefore, can be equal to -1, 0, and 1. All right. Now, remember, for the way we wanted to solve this problem, we chose the higher wavelength, which corresponds to the lower final energy. So we took energy away. That's a negative. We took energy away. And so that is going to correspond to ml being equal to -1. If we did the lower wavelength, that would be ml equals 1, and ml equals 0 corresponds to no magnetic field interaction, and that is just our base wavelength. So we now know that ml is equal to -1 in our example, and the magnetic field B is going to be equal to -0.0017 electron volts divided by -1 times the Bohr magneton, which is 5.788 times 10 to the -5 eV per Tesla. We see that our units cancel quite nicely, and we will get this in terms of Teslas. Plugging that into the calculator, we end up with 2.9977 Teslas, which is just about 3. And that's our answer.